Well, welcome back, ladies and gentlemen. Boy, do I have a big one for you tonight. Look at all the topics we're covering. We've got functions, one-to-one functions, onto functions, composition of functions, and inverse functions. And as you found out from our Grizzly last week, these are all pretty big topics on our exam, and they pop up and we just got to know them when we see them. So I apologize that it's a little on the lengthy side, but take your time, it will pay off. So let's start off by talking about a relation. So this is the first definition we want in your book here. A relation is simply a set of ordered pairs. For example, if I write the ordered pair 2, 3, that's considered a relation, a set of ordered pairs, or 1, 5. Now, on top of that, we have the definition of a function, and that's our big topic that we've talked about quite a bit this year. A function is a set of ordered pairs in which each x element has only one y element associated with it. And that's the big deal. Each x has only one y. So let me give you an example of something that is a function. Let's take the set 2, 3, 4, 6, and 5, 3. This is an example of a function. Every x value has only one y value. 2 is paired with 3, 4 is paired with 6, and 5 is paired with 3. Now, even though the y values are the same, that doesn't matter. Each x has only one y. If you're finding that hard to bite, think about this. A function has to pass the vertical line test. And what that says is each vertical line drawn through the graph will intercept a function in only one location. Okay? So if you're not buying that this is a function, you could easily plot these points and think about it. If I plot 2, 3, 4, 6, and 5, 3. If you were to draw a vertical line through each one, does the vertical line only hit your point once? I would say yes, so that is a function. So another way to think about it is every x must be different. Okay, I don't really care about the y value, but every x must be different to be a function. So let's take a look graphically at the vertical line test. In example 1 here, we have a nice sketch of a parabola. So I would say that's the graph of y equals x squared. Okay, and obviously I have a nice graph drawn for you. And I drew these lines in here. You can see that this line only hits your parabola once. This vertical line only hits once. This vertical line only hits once. In fact, if I were to take my vertical line and swing it across, do you see how it's only ever hitting my graph once? Okay, no matter where I move it back and forth, it's only hitting once. Therefore, we can title this graph a function. Again, it passes and will abbreviate the vertical line test. Let's do the same with the graph next door. This is a graph, hopefully that looks familiar. This is a graph of y equals e to the x. Remember, exponential grows very, very fast, and it passes through that special point 0, 1. So I can take my same vertical line and see if it passes the vertical line test. So you'll notice as I swing my vertical line left to right, it only ever hits that graph once. So again, I have another example of a function. My reasoning passes the vertical line test. I've got 2 more quick examples for you here. On this picture on the left, you can easily see that my vertical line hits in 2 spots. Therefore, this is not a function. And my justification, of course, is it fails the vertical line test. The graph on my right, you'll notice I just have points plotted. I've got this point, this point, this point, this point, and this point plotted. And you'll see that when I draw that vertical line, it hits 2 points on top of each other. And again, the vertical line test can only hit the point once. So again, I would say this is not a function, fails the vertical line test. Again, just a few more examples. This one, I'll just title it 1 for the time being. Is this set of ordered pairs a function? And again, the rule was every x can only have one y. Every x can only have one y. And the way we said it, it was basically every x had to be different. Are all of my x values different? And that answer hopefully is clearly no. And again, I just want to stress, if you ever get stuck, just plot these points. If you graph 2, 4, and then try to graph 2, 5, can you see that that's not a function? My vertical line is going to hit that twice. So this is not a function. Again, every x has to be different. In example 2 here, I've got 3, 6, 1, 3, and 3, 5. My question is, what could you put in place for x that would make it not a function? What could x be so that it's not a function? Could I put a 2 there and this would not be a function? Well, would every x be different? Yes, so that would be a function. What could I put there so it wouldn't be a function? I think my answers are either only 1 or 3, and I hope you would agree with that. In this last little bit about functions, I just want to talk about mappings, and that's when you see these two circles drawn out and they're mapping something to something. So I think it's easiest if you just kind of list out the points they're mapping. For example, they're saying 1 goes to 2, so I would just write the coordinates down, 1, 2, 3 goes to 2, 5 goes to 7, and 9 goes to 8. So is this a function? Does it follow our rule that every x value has to be different? Every x can only have one y. And I would say yes, this is a function. All right, I've got two more big function names for you. This first one is called a one-to-one function, and we haven't used this term in a long time, and my guess is you probably saw it on your Grizzly last week. A one-to-one function, and we'll jot these both down, is when every y value must be different. So just a regular function, every x value must be different, but in a one-to-one function, every y value must be different. It's kind of like going backwards. And if you're looking at it graphically, it has to pass the horizontal line test. So let's take a look at our first example. All right, so I'm not going vertical line test. I want to tell if this is one-to-one. So I'm just going to take my horizontal line, sweep it through, bam, right there. I think you can see that it hits twice. Okay, it fails the horizontal line test. All right, so I just want to be clear that this is not a one-to-one function. All right, this is not one-to-one, and again, I'm abbreviating it with 1-1. Let's try this mapping over here. Okay, again, if it helps, write them out. R goes to 4, H goes to 2, O goes to 1, and Q goes to 5. All right, is this a one-to-one function? One-to-one, remember, I'm looking at the y values. Are every y value different? I would definitely say yes, so I am going to make a note. This is a one-to-one function. Again, if you were to plot them, you are looking for it to pass the horizontal line test graphically. Let's take a look at this last example. Again, I'm going to write them down. R goes to 4, H goes to 2, O goes to 2, and Q goes to 5. Do I pass the one-to-one test? Is every y value different? Heck no. I see these two are the exact same. So this is not one-to-one. Remember, every y has to be different. Is it just a plain old function? Yes, because every x is different, but it's not a one-to-one function. All right, our next big function that we haven't talked about in a while are onto functions. Okay, so these are your definitions here. Every value in the range is used, and what do I mean by that? Well, basically our range goes from positive to negative infinity if I'm looking at it graphically. Let me give you an example. All right, example 1. Is this an onto function? And again, that meant, graphically, my range goes up to positive infinity and down to negative infinity. Would you say that's true? Does this graph go up forever and down forever? And it doesn't skip anybody, so I would say that this is onto. And again, that's because my range goes from negative to positive infinity. Is it just a plain old function? Okay, when you see just the plain old word function, you're looking for the vertical line test. Does it pass the vertical line test? I would definitely say true. If I draw in a vertical line, it only touches once. How about a one-to-one function? This time it has to pass the horizontal line test. What would you say about that? I would definitely say true again. So this one is all three. Onto a regular function and a one-to-one function. Let's try example 2. Is it just a plain old function to begin with? All right, so plain old function, vertical line test. I would definitely say yes. Is it a one-to-one function? Does it pass the horizontal line test? We'll draw one in. No. So it is not one-to-one. How about onto? Does the range go from negative to positive infinity? Does this graph go up forever? Absolutely. But does it go down forever? I would say no, it stops right here. So this is not onto, just a function. Let's do two quick more with a mapping. All right, so I'm going to write them out real quick. R goes to 4, H to 2, let's see, O to 1, and Q to 5. All right, so is it a plain old function? What am I looking for? I need every x to be different. R, H, Q, O, definitely. Is it a one-to-one function? This time I need every y to be different. Let's see. Whoops. 4, 2, 1, 5. Check. Is it an onto function? Okay, now graphically we can't see if it goes to positive and negative infinity, but here's the deal. Basically, did we use all numbers in the range, in the y value? Did I use all numbers in the range or the y section? Well, if this is x and this is y, did I use all of them? Yes, somebody is going to all of them, so this is onto. And our last one, let me write them out again. I've got R to 4, H to 2, O to 1, and Q to 5. Okay, so is it a function? Every x is different. I can check off function. Is it a one-to-one function? This time I'm looking at my y's. Is every y different? Check. Is it onto? Did I use everybody in the range? Did I use everybody in the y value? Well, I would say it's not onto, because look at this. This 8, there's nobody going towards him. So I just want to be clear that this is not onto. I did not use everybody in the range. Our next mini topic is just function notation. So I want to be clear that a lot of times in algebra you've said y equals, we'll say 4x plus 3. Okay, now function notation, instead of saying y equals, we just use f of x equals 4x plus 3. And what is this implying? Well, this variable that they have inside here, okay, it's important. This is telling you the variable that will be used in the problem. So if I say f of x, then I need to be using x in my problem here. However, if I said f of m, then instead of saying 4x plus 3, my equation would be 4m plus 3. Okay, so this is telling me the variable used in my problem. Likewise, I could use any letter I want here. I could say g of p. Okay, so that's just telling me 4p plus 3. Okay, so all of these things mean the same thing. And again, the variable in the parentheses is the variable I should see in the problem. If they wanted to call it, g theta, I would say 4 theta plus 3. No big deal. Again, this is just identifying the variable in my problem. Example 1, a function is represented by f of x equals 2x plus 3. Find f of 3. So watch what I do. I'm just going to replace this x with the number 3. So I would say f of 3 equals 2 times 3 plus 5. Notice I'm just taking this number and substituting it into every variable I see that's x. So f of 3, 2 times 3 is 6 plus 5 is 11. 2, find the value of h of x equals 2x squared plus 6x minus 3 when x equals 4a. So same idea. I would just say h of 4a equals 2. Notice when I substitute in, I'm always using parentheses. 6 times 4a minus 3. And now I'm just going to carefully clean up. Just remember order of operations. Parentheses and exponents come first. So I would say I have 2 times, square everybody, 16a squared plus 24a minus 3, which gets me 32a squared plus 24a minus 3. Now, some of you, we've noticed, like to create extra work for yourself. Basically, this is your answer. Don't try to factor it and go further. It just says find the value of h of x. It doesn't actually say solve h of x. So you are done right here. And just one last one for function notation. Find f of 3h plus 2 when f of x equals this. So again, I'm just substituting this junk in to the letter x. F of 3h plus 2 equals 3h plus 2 squared plus 2 times 3h plus 2 minus 1. So every place I saw an x, I substituted in 3h plus 2. Now, to solve this, very simple. I just have to FOIL this out. So basically, when you see something squared, you should be writing it twice, unless you can FOIL in your head. That would be awesome. So I've got 9h squared. That's going to get me 6h plus 6h is plus 12h plus 4 plus 6h plus 4 minus 1. Looks like a total of 9h squared. It's 12h plus 6h. Gets me 18h plus 4 minus 1. 8 minus 1 is 7. Topic 2 this evening is called composition of functions. And composition really just means to combine functions. Okay, so the notation we've used in the past looks like this. And I just want to take note that this is red f of g of x. So this is f composed or of g of x. And basically every time you see a parenthesis, we're saying the word of. F of g of x. Okay, so these two things mean the exact same thing. They can just be written two different ways. Example 1. Given the functions f of x equals 5x and g of x equals x squared plus 1, we're going to find two things. Let's start with a. And again, just practice reading it out loud. It says f of g of x. Okay, f composed of g of x. Now the whole key to composition of functions is you're actually going to work right to left. Alright, so let's put that in our notebook there. Work right to left. So watch how I rewrite this. I'm going to say this is f of this function. I'm working on the right side first. F of g of x. Now, I'm just going to use some substitution. I know g of x is equal to x squared plus 1. So I'm going to say this is f of x squared plus 1. Now, I'm just doing simple function notation, and I'm taking x squared plus 1, and I'm substituting it into f. So I would say this is equal to, here's my function f, 5 times x squared plus 1, which of course is just 5x squared plus 5. So, like I said, let's just work right to left and take your time. Let's try part B here. Again, read it as you write it. It says g of f of x. Okay, or g composed of f of x. So I just want to stress we're working backwards. So I'm going to start with this thing that I boxed in on the right, f of x. Okay, which is, if I arrow up here, that's my 5x. So I'm just going to rewrite this. This is actually g of 5x. So now I'm just going to take my 5x and substitute it into g. Okay, so I've got 5x squared plus 1. Every place I see that x, I'm substituting it in. Now, let's be smart. When we have stuff in parentheses and there's no plus or minus, we're just going to square everybody we see. So this becomes 25x squared plus 1. Number 2. Given the functions, we've got p of x and h of x, find h of p of 3. Okay, so I'll do one more with you. We're working right to left, so box the thing in on the right, and let's rewrite this. This says h of p of 3. Okay, so I've got to take 3 and plug it into p. Remember, we work backwards, right to left. So if I plug 3 into p, I'm going to get h of, okay, so I'm just plugging my 3 in here, 3 plus 2, which is really just h of 5. Now I've got to find h of 5, so I'm plugging 5 into this term, and that looks like 5 squared, which is 25. All right, last one here, h of p of x. All right, pause it, see what you get. All right, see if you like my work here. I rewrote it as h of p of x. Okay, so here's my right term, wrote it in here. And then I said this is really h of x plus 2. That's what p of x is. So basically I said, what is p of x? And I put it in there. And now I took x plus 2 and substituted into h. And that would be this step here, x plus 2 squared. Now notice, because there's a plus sign, you can't just go around squaring terms. You have to FOIL. So this time I had to write it twice. X plus 2 times x plus 2. And I've got x squared plus 4x plus 4. Our next topic is called inverse functions. So one way to think about functions is this line here. A function and its inverse can be called the do and the undo functions. And for example, here's our true definition of inverse. If I compose f of g of x, and that's equivalent to the same thing as g of f of x, and that is equal to x, then I can say f and g are inverses. So let me say that one more time. If you take g and compose it into f, substitute it into f, and you take f and compose it into g, and they both turn out to be x, that means f and g are inverses. If they don't turn out to be x, then they're not inverses. It's just a quick way to check. But again, this is our true definition of inverse function. So you might be thinking, how do we find the inverse of a function? And that answer, of course, is switch the x and y and solve for y. So let's run through a few quick examples. Number 1. Given function f, find the inverse relation. Is the inverse relation also a function? So there's two questions here. The first thing they want us to do is find the inverse. And hopefully you'll recall that notation for inverse is f inverse, and it looks like an exponent of a -1. If you picture sine and sine inverse, they're on the same button on your calculator. It says sine x to the -1, cos inverse, tan inverse. So the notation again for inverse is f to the -1 there, or a function to the -1. And it's very simple. To find the inverse, I just follow these directions. Switch the x and y. So the inverse function, I'm just going to take this point 3, 4 and follow the rule. Switch the x and y. So that becomes 4, 3. Notice nobody said anything about making anything negative or switching signs. You're literally just switching the x and y. 1, -2 should become -2, 1. 5, -1, -1, 5, and 0, 2, 2, 0. Now the second part of the question says, is this relation also a function? Okay, so let's go back to our definition of function. Every x value had to be different. Every x can only have one y. So I'm just going to box in my x values. I have a 4, a -2, a -1, and a 2. Do I have a function? Is every x value different? I would definitely say yes, this is a function. Remember, if there's some reason you can't tell if every x is different, plot the points and see if they pass the vertical line test. And as long as they pass that vertical line test, you're in good shape. And clearly, I tried to plot them real quickly, you can see that those pass. Now, you'll notice I didn't follow the rest of the directions that said solve for y because I didn't have an equation. Let me tweak the next question. Find the inverse given f of x equals 4x minus 5. Now, I just want to recall, this is just fancy notation for what variable? Y. I'm going to rewrite my equation as y equals 4x minus 5. Now, I haven't found the inverse yet. I haven't switched my x and y. I just want you to understand that f of x is really just y. Okay, so now to find the inverse, we're going to switch the x and y. And lastly, I just have to solve for y. Just some nice easy steps. How would you move the 5 over? Well, I would add it. X plus 5 equals 4y. And then lastly, divide by 4. Now, here's what they can do on the exam. They can strictly say, okay, that's everything divided by 4. So you could say y equals x plus 5 over 4. Or typically what we like to do is we like to divide each term by 4. So let me go back here. If I said x plus 5 equals 4y, I can divide every term by 4. Okay, so I also have y equals x over 4 plus 5/4. These are the exact same thing. This one's just dividing the whole fraction by 4. This is dividing each term by 4. Number 3, find the inverse. F of x equals x cubed minus 2. Why don't you pause it, try it on your own, and see if we get the same thing. So I rewrote mine as y equals x cubed minus 2. Again, f of x is just y. Here I've switched my x and my y. and moving my 2 over. My goal is to get the y by itself. I have this goofy looking cubed. How do you get rid of a cube? Well, the inverse would be taking the cubed root of both sides. And notice I'm doing it to the whole side, not to each term, the whole side. So those cancel, and I would say y equals the cubed root of x plus 2. All right, I've got one last inverse one, and then we'll switch gears again. Find the inverse of f of x equals x squared minus 2. Now this was an old exam question, and this got a lot of us last year on the exam. So pause it, try it on your own, and see if you catch the little hiccup at the end. Well, hopefully your work agrees with mine, and here's where the big deal came in last year that we missed on our exam. If I want to get rid of a square, I would now just take the square root of both sides. But, like I said, here's what we missed. Every time you physically put your own square root in, okay, not if it already exists, but when you take your own square root, what goes in front of it? How many answers should you get? You've got to get a plus or minus the square root of x plus 2. Okay, so let me come back and just take a look at this previous one up here. I didn't need to do that for the cubed root. Okay, remember, cubed roots don't get the plus or minus, but even roots do. Square roots, fourth roots, sixth roots. Even roots get that plus minus, and odd roots don't. All right, our last section tonight is inverses graphically. Two things we need in your notebook here. If a function passes the horizontal line test, it has an inverse. So this is a quick way to check to see if a function has an inverse. And second, a function and its inverse are reflections over the line y equals x. All right, so does this function have an inverse? Well, my goal is just to see if it passes the horizontal line test. And watch me move my horizontal line. Is it only ever touching in one spot? I would say yes. This passes the horizontal line test. Okay, so passes the horizontal line test. That means that this guy has a function that's an inverse. Now that we know it has an inverse, let's go ahead and graph its inverse. And remember, all inverse means is switch the x and y. So let's take a point we know. Let's take this point 0, 2. Okay, if that's on f, what is f inverse going to be? Switch the x and y. I would say 2, 0. Plot that point. Let's take another point. 1, 6. If 1, 6 is on f, what is going to be on f inverse? 6, 1. Let's plot that point. And lastly, let's take this point, negative 3, negative 6. If I want to be on f inverse, that's going to be negative 6, negative 3. We'll plot that point. And now we'll try to connect them as smoothly as possible. So there is the graph of my inverse, and I'm just going to label it f inverse. And I also want to show you that it is a reflection over the line y equals x. If I were to graph y equals x, that means whatever I pick for x, I also have to pick for y. So example, the point 1, 1, the point 2, 2, 3, 3, 4, 4. Okay, so let me go ahead and draw in y equals x. And do you see how it's a reflection over that line? This black line, if I flip it over my red line, should land right on my blue line. So I have an inverse and a function graphed.